Hello, we're going to look at some double angle formulas, and then eventually in some other videos you'll see power reducing half angle. But this video we're going to look at the double angle formulas for sines, cosines, and tangents. So these were the sum and difference formulas from last one of the previous videos, and I'm going to look particularly at these two right here. Now double angle means that we are going to look at something like the cosine of 2 times an angle. Okay, well, where I'm going to get this from is 2 times an angle is the same thing as that angle added to itself. And so if I start off with theta plus theta, I can use this formula. So the cosine of theta plus theta, if I plug in here, I'd have theta in this position, so let's say that's that theta, and then I'd also have theta in this second position. So let's say that's that theta. All right, and so just to distinguish them, there's alpha, so that's like the theta that was in the alpha position. There's alpha, so that's that guy right there. And then this is the beta, all right, so that's the second one. But because it's the same in both places, these are the same here. Cosine theta, that's just cosine times cosine, which is cosine squared theta. And the same thing with the sine. So what we get is the cosine of 2 theta is this formula right here. Now, because of the Pythagorean identities that we've seen in previous videos, we can manipulate that Pythagorean identity and isolate either cosine by subtracting the sine over, or we can isolate sine squared by subtracting that cosine over. So cosine squared is 1 minus sine squared is 1 minus cosine squared, so I can write this cosine squared theta as 1 minus sine squared, so this would be 1 minus sine squared minus another sine squared, so I could say that's 1 minus 2 sine squared theta. All right, so that's equivalent to cosine 2 theta. And then we also could say, going back to this original identity we get just from replacing alpha and beta up here with theta in both positions, we could, instead of replacing cosine with 1 minus sine squared, we could also replace this sine squared theta with 1 minus cosine squared. So then we would have cosine minus 1 minus a minus plus, so we end up with 2 cosine squared theta minus 1. If we replace that with this, we'd have a minus 1 plus cosine squared, so we end up with 2. So there's actually 3 forms of cosine 2 theta based on the, again, just plugging in theta into both positions for the angle in the sum formula, and then just using that Pythagorean identity on that, we get these 3 different forms. And notice the 3 different forms, one has both sine and cosine, one has only sine, and one has only cosine. Okay, but we have double the angle here and just the angle by itself in both of these places. Now if we did the same thing with sine, same thing if I did sine of 2 theta, which is theta plus theta, again like we did with cosine, I would then do the same thing. I would replace theta and theta. So I'd have a theta here, a theta here, a theta here, and a theta here. Well, notice this is sine theta cosine theta, and so is this cosine theta sine theta. If I reversed it, I'd have sine theta cosine theta in both places. So the sine of 2 theta is 2 sine theta cosine theta. And so we get this other doubling identity. So there's cosine 2 theta, could be any one of these things. Then sine of 2 theta is 2 sine theta cosine theta. Alright, so there are double angle formulas for sine, cosine, and then tangent. Tangent just comes from, you remember tangent is sine divided by cosine. So if I take this guy right here and divide by this, alright, all I have to do is simplify, and you'll see that this comes directly from this. I can take that bottom down there, and notice this is cosine squared, this is 1. If I divide top and bottom by 1 over, or sorry, multiply top and bottom by 1 over cosine squared theta. Alright, as long as I do the same thing at the top and bottom, it's legit. What's going to happen is, down here on the bottom, cosine squared times 1 over cosine squared is 1. sine squared times 1 over cosine. That would put the cosine squared down below the sine. That gives me tangent. And then notice what's going to happen here. I'm going to, one of these cosines, I'll cancel out this cosine, and the other cosine I'll multiply by the sine. So 1 over cosine times sine is sine over cosine, so I get a tangent. So 2 tangent from that, the cosine cancel with the other cosine down here on the bottom. And then multiplying through there, I get this. So it's just taking these two things and dividing them. Sine 2 theta divided cosine 2 theta is tangent 2 theta. And then this divided by this, we just showed that if I multiply top and bottom by 1 over cosine squared, I get this expression. So there's an equivalent expression for tangent 2 theta, just coming from simplifying the double angle formulas for sine and cosine. All right, so let's use it. Let's look at a picture. We got a, I'm going to look at the unit circle. All right, and it says that we are in quadrant 2. So there's my x-axis, there's my y-axis, and it says I'm in quadrant 2. So remember, this is quadrant 2 over here. All right, and the sine is 5/13. Okay, remember sine, if I put a point, I'm just going to put it arbitrary. Notice the sine is opposite over hypotenuse, so the hypotenuse opposite. So whatever angle I'm in, let's call it that angle. That's a little bit too big. Let's call it right to there. There's theta. All right, so that's 13. That's the hypotenuse, and then the height is 5. All right, so opposite over, that would be our theta. That would be our reference angle right there. But opposite over hypotenuse, 5 over 13. What is this going to be? Well, you can do the Pythagorean theorem. You'll end up that this is 12. But because we are in quadrant 2, we went this way. So that's a negative 12. Okay. Even though the distance is 12, the coordinate of that point, we could call it negative 12, 5. Okay. And that would kind of give us an idea of what all the values are going to be. All right. So knowing what we've got sine of theta is positive 5 over 13. Well, the cosine of theta is equal to negative 12 over 13. It's adjacent over hypotenuse, so negative 12 over 13. And then the tangent of theta, it's sine divided by cosine, which is this divided by this. Well, flip and multiply, and you would have 13 over negative 12, so negative 5/12. All right, and that's our sine, cosine, tangent. Now, why is that important? Well, we can find sine, cosine, and tangent of the double angle based on sine, cosine, tangent of the single angles. Just go back and look at the formulas. There's how we're going to get these. Let me erase derivation of the sine, tangent double angle. But how am I going to get the sine of 2 theta? I'm just going to plug in sine and cosine of the original angle measures in both of these positions. All right, so let's go through. Sine of 2 theta, that's 2 sine theta cosine theta. So that's equal to 2 sine theta is 5/13. All right, cosine theta is negative 12/13. So we end up with 2 times 5 is 10 times negative 100, negative 12 is negative 120 over 13 times 13 is 169. So negative 120 over 169. Now, a calculator can help with this somewhat. You've got to be able to think on your toes. But if the sine of theta is equal to 5/13, I can do arc sine of 5/13, and that'll give me the angle. Now notice the angle that it gives me, this is 22.61 degrees. But that would be in quadrant 1. Remember, arc sine can only give you quadrant 1 or quadrant 4, and give you this if it's a positive angle, this if it's negative. But I'm in quadrant 2, so 22.62 roughly degrees, that's down here. What angle is that equivalent to over here? Well, it's 180 minus that. So 180 degrees minus that angle, that's the actual angle we're dealing with. That's the quadrant 2 angle that has this as its sine. So if I did, what's the sine of that 157, oops, what's the sine of that 157 degree angle, I get 0.3841 blah blah blah. What's this, what's 5/13? Alright, it's that same number. So the sine of 157 degrees is the same thing as the sine of that 22.62 roughly. I'm going to round it. Alright, it's basically that same thing. It's just because we're in quadrant 2, we can't just use arcsine. We have to alter it. Okay, so what did I do? I did arcsine of 5/13. Alright, that's my quadrant 1 version of that angle, but because I'm in quadrant 2, the angle that has that same sine, 5/13, that's in quadrant 2 would be 180 minus that. Okay, it's the supplement basically, if you want to call it that. Now, why is that important? Well, this is the angle, 157.3. This is the angle that I'm dealing with. This is theta in quadrant 2. So if I double that angle, I'll have the angle that I'm looking for. So 314.76, and now I can take the sine of that thing. The sine of that answer is negative 0.7100, and I can see that that's the same thing as negative 120 over 169. Right? I'm getting the same thing. Okay, now you may be saying, all right, well, but why is that? Why can't I just do that? Why do I have to draw all these pictures? Well, it's to get the signs right, to get the numbers right. Right? Without drawing your picture correctly, if you just start typing stuff into your calculator, the cosine won't be negative if we don't realize that we're in quadrant 2. If we dealt with just that 22 degree angle, we're in quadrant 1, right? And if we're in quadrant 1 and double that angle, like if I just completely ignored the fact that I'm in quadrant 2 and I did the arcsine of 5/13 to get my angle, I would get that 22 degree angle. And if I double that thing, I'm still in quadrant 1. And if I take the sine of, that's 2 theta, if I'm thinking theta is that original angle, if I take the sine of the original of this, thinking that this is 2 theta, the problem is I don't get a negative, I get a positive. Alright, so the fact that we're in quadrant 2 is everything here. It's what's going to get you your signs right. You're not going to get partial credit for not having your signs right here, because this is telling you some really important information. Doubling this angle versus something that would have this same y coordinate back in quadrant 1 goes from an acute angle doubled, now we're in we're still in quadrant 1, versus an obtuse angle doubled gets us all the way down here in quadrant 4. Okay, so it's very important that you use this information given. Very important. Alright, B, the cosine 2 theta. Cosine 2 theta is cosine squared regular theta, not 2 theta, minus sine squared regular theta. The cosine of theta was 12/13, so I'm going to square that. That's negative 12/13 squared, minus sine was 5/13 squared. Okay, 12/13 squared is 144/69, or 1/69. 5/13 squared is 25/169. Alright, and then 144 minus 25 is 119/169, and it's positive. Alright, that's the cosine of 2 theta. So again, this is theta. If we rotate that again, we get down here and like to quadrant 4, just barely. And that point, what we're saying is 119/169, comma, negative 120/169. So the x coordinate is positive, right, and the y coordinate is negative. Again, if we did the arcsine of the 5/13. All right. That's the equivalent first quadrant angle. We're in the second quadrant though, so we subtract from 180. All right, so there's my quadrant 2 angle with the same 5/13 as the sine. This is 2 theta. All right, this is 2 theta. Or sorry, this is theta. Now times 2, it's 2 theta. Now if we take the cosine of this thing, all right, the cosine of that angle, we get this 0.704, which if we dial this in, 119 over 169, there's that 0.704 again. So we can check our answer, understand this, but we got to understand, why are they giving me this? Because it's vital. You have to know reference angles and the fact that arc sine and arc cosine put you in different positions on that unit circle. All right, now tangent, I can do a couple of things. I can plug into the tangent formula, and I will in just a second, but remember tangent 2 theta is sine 2 theta over cosine 2 theta, and notice that both of these have 169 involved. So for tangent, I'm going to get negative 120 over 169 divided by this guy, which is the same thing as multiplying by the reciprocal. And those 169 cancel, so we end up with negative 120 over 119. Okay, so that's the easiest way to get it, in my opinion, is just to use the sine and the cosine. It's the numerator here divided by the numerator here. But you can also get it using the negative 5/12 from the original formula with this formula right here. So this was negative 5/12. So is this, we're just going to square it, okay, because it's being squared. So we get 2 times negative 5/12 over 1 minus negative 5/12 squared. All right, that's going to cancel and leave me with a negative 5/6 up top, divided by 1 minus 5/12 squared is going to be 25 144ths. All right, so that's negative 5/6 on the top. 1 minus 25 over 144 is going to be 119 over 144. And then dividing, once again, we're going to multiply by the reciprocal. So negative 5/6 times, flip and multiply, we get a 144 on the top. We get a 119 on the bottom. And then we can reduce. All right, 6 goes into 14 2 times, remainder of 2. 6 goes into 24 4 times. And then negative 5 times 24 is negative, that'll be 120 over 119, which is what we got right here. All right, so again, that's the easiest way. If you've already done sine and cosine, just divide those two to give you a tangent. That'll always be tangent. But you can also plug into that formula if you ever have one where you don't have to compute sine and cosine first, and you do know the tangent of the original angle measure, you can plug in. Okay, but a problem like this is so important. You can't just start using arc sine to get your angle. You can, you just have to put yourself in the correct quadrant to be able to do it. Okay, you just got to make sure that you're in the second quadrant and you adjust to the fact that you are there if you do use arc sine. Okay, you got to get yourself in the correct quadrant, so you got to understand why this is being given to you.